All right, so last time we were talking about symmetries of SCT. We talked in detail about gauge symmetry, and we'd started to talk about reparameterization invariance, and we're going to continue with that today. So reparameterization invariance in SCT is kind of rich because we have lots of things that are messing up Lorentz invariance. But we started out talking about three different types here. One where we rotate the physical n vector that was the direction of our collinear particles to some other vector that's equally good, which I call n prime in the figure. That was a type 1 transformation. Or we could change this auxiliary vector n bar by a large amount. That was type 2. Or we could change both n and n bar in a way that dot products remain invariant. That was type 3. So all three of these preserve these relations, n squared equals 0, n bar squared equals 0. N dot n bar equals 2. And really, these transformations are just giving us a different basis for our decomposition, which satisfies all the things that we wanted that basis to satisfy, doesn't change any of our power counting, and so is an equally good description for the effective theory. And therefore, we want to have invariance under these transformations. So we're restoring Lorentz symmetry in this way. We break it by introducing these vectors, but we're restoring it in a way by having transformations on these vectors. But it's not, you're not restoring, if you like, it's still different than Lorentz symmetry, for example, because you're not making huge transformations of the vector n here for not any arbitrary transformation. And it is a reparameterization, not a Lorentz symmetry in general. So we'll talk more about how this connects to the HQET one in a minute. But if we have a vector, then obviously the vector p mu, if I don't write the right-hand side, is invariant to what choice of basis I use. Right? So that means that this p mu should not change. And that means if I change n here, let's say I do a type 1, then I'll change n here and I'll change n here. But I must compensate those changes by changing what perp also depended on the meaning of n, so there'll be a compensating change from the perp. So we can figure out from statements like this what the transformation laws are. So this guy is invariant to the decomposition. So the transformation of p perp mu compensates for n in type 1 or n bar in type 2. Type 3 is already invariant because we have an n and an n bar here and an n and an n bar here. So that's type 3 invariant already. So if we go through that, we can make a table of all the different transformations, and we can derive the transformations. We also have to do the same thing that we did in HQET, because the other important fact is that we have a projection relation right here. So we also have this. And you'll remember that when we talked about reparameterization invariance in HQET, the projection relation was part of the discussion. And so that's true too. But let me just quote to you the results, and you can kind of get an impression for where these various terms are coming from. So let's summarize first type 1. So type 1 was n goes to n plus delta perp. So if you have something like n dot d, that goes to n dot d plus delta perp dot d. There's a transformation of p perp or d perp. Let me write it as d perp. This is really for any vector. Which has to compensate for the transformation of the n in the way I described. There's a transformation like that. The n bar component under type 1 does not transform. And if you go through the spinor, or if you go through the field, the fermion field, it does get, because the projection relation has a transformation, there's a transformation of this guy. The Wilson line, which we talked about, was up only a function of m bar dot a, and so it doesn't get transformed. So that's what type 1 transformations would look like. And type 2 summarize. They start out looking the same, and then there's some differences. So everything so far looks exactly the same as type 1, just with a sort of suitable replacement. But the fermion ends up looking a little more complicated here. And the Wilson line also transforms, because the Wilson line was built out of n bar dot d field, so working to first order in that transformation, there's an additional term, epsilon perp dot d perp. Okay, so I didn't want to take you through the derivation of all these equations. I have provided references. There's a reference list at the beginning of the notes, and there's a reference with a paper that talks about how to derive these equations. We won't be spending too much time talking about it, so I won't go through the derivation, but it's very analogous to what you would do in HQET. So how do we use these results? Let's take them as given. We can use these results to close out our discussion of what we were talking about last time and show what the leading order Lagrangian is, imposing all the symmetries. And so the first thing that we can note is that if we do a type 1 transformation, of this guy, and we simplify the result, then at the end of the day, that boils down to just the following. So it can be simplified to a single term. And if one does the same thing on this guy, then that gives us the same term, but with the opposite sign. So these two operators are connected by reparameterization invariance. The sum of them is reparameterization invariant, and that looks good. So the sum is 0, connected by RPI, and that means, for example, that you couldn't have any non-trivial Wilson coefficient between them or anything like that. Now, if you go through the same argument with the other operator that we talked about last time, where it was d perp mu, so delta 1 so same thing as above, but just having d perp mu, d n perp mu. You actually find that it gives the same result as this. Okay, so if you just have reparameterization of type 1, then you can't really, the sum of this and this would be invariant, or the sum of this and this is invariant, or the sum of any combination of it, 1 minus a times that and a times this would be invariant. But type 2 does distinguish between this operator and this operator. if you do a type 2 transformation, you get terms from this that you can't possibly cancel by any other term that you could write down. And those terms are such that the power counting, there's not a subleading operator that could compensate either. Okay, so going through all the type 2 transformations is kind of messy, so again, I don't want to do that, but I will refer you to some reading for that. Okay, but if you take these two things together, then you do rule out that additional operator, and so then taking everything together, we have a unique leading order Lagrangian. It's not so easy, actually. It requires looking at the transformations carefully. Yeah, so it is. So even though I made it sound like it's simple, but it's not, there's a reason why I don't want to spend the rest of the class on it. Okay. So if we put all the things that we've talked about last time and this time together, then what we find is that this Lagrangian that we've been discussing is unique for the CN field. So it's the unique leading order Lagrangian for the CN field. And the things that we've used here are power counting in order to say that the terms here should be lambda to the fourth. That's what leading order meant. Gauge invariance to make these covariant derivatives of appropriate types. And now also reparameterization symmetries. So as we kind of discussed last time, the reparameterization symmetries here can do different things. They can connect leading order operators to leading order operators and hence constrain the form of leading order operators you write down, and that's what we just did. And in particular to the type 2, remember the epsilon perp was order lambda to the 0, so maybe it's not surprising that that's what it's doing. The type 1 transformation, the delta perp, took you down a power in lambda, but if you had some subleading operator, then it would also take you down a power in lambda. So you have to, that's one of the things that you have to be careful about when you're sort of counting powers of lambda. But there is a sense also in which reparameterization symmetry does the same thing as HQET, which is it connects. So it can do two different things. It can constrain the form of operators you write down at lowest order, or it could connect the Wilson coefficients, for example, of leading order operators to subleading operators. And that's what we saw on the problem set in the HQET example. It can do that here too. And so if we want to think about that freedom, then we should note that there's actually more kind of reparameterization than we've talked about just with this example. So far what we've talked about is changing the basis. But we could also change the amount of the momentum that we stick in the label versus the residual. That was also a choice that we made in doing things. And we should be careful to think about that freedom as well. And that's also a reparameterization freedom. And this one looks in some sense more like what we talked about in HQET. In some sense, what HQET is doing is a combination of these two things, because the decomposition of momenta there is a bit simpler. So we had this split of label and residual momenta. We thought about the labels as discrete. But still, even if they're discrete, there's a freedom in how we make this split. And so we could, if you like, take our label momentum or our label momentum operator and transform it by adding some beta, which has a power counting of order lambda squared. And if we make a compensating transformation in the residual momentum or the residual derivative, then that would be a symmetry of the decomposition. Wouldn't change anything. n dot beta being 0 projects us onto these two cases. So if you wrote that as a change to the field, then you'd be saying that the field picks up a phase. That's the transformation for the derivatives. And then you could shift the label by beta. That's the transformation for the beta, for the label. OK, so this is a different transformation than the ones we were talking about over there. And it's a transformation that has to do with this freedom. But basically what this freedom does is it connects the derivatives to each other. So it connects this combination. It does something very simple. So after you know what it does, it's simpler just to say what it does and forget about thinking about it as a transformation. It simply connects the label operator to be label operator plus the derivative operator. OK? But these two have different orders in the power counting. And so what this will do is it'll connect things that are leading order to things that are subleading order, for example. One way of saying that is that it connects leading and subleading Wilson coefficients, because you can always think of the coefficient as the thing being fixed. And then it would do it in both something like a leading order to subleading order Lagrangian, or if you also wrote down operators, if you wrote down a series of some external operator, maybe it's a weak interaction, then it could connect, as we saw in the problem set, it could connect C1 to C0 like it did in HQET. OK, so this one clearly does that. So after you see that, then you should think about the following thing. Well, this is reparameterization symmetry. What did reparameterization symmetry do here? It connected label and residuals to each other. It said, well, they were both part of the same thing in the beginning, so there should be some connection later on in the effective theory, and that remains true. And it's encoded in this reparameterization symmetry. But you can also now try to think about, given that we have these derivatives, what about gauging that formula? Right? Gauge symmetry basically was telling us how to turn p mu into a covariant derivative and partial mu into a covariant derivative. So can we think about combining what we know from gauge symmetry together with reparameterization? And we actually can, if we're careful. And where this is leading is we'll find that there's basically, in the end of the day, there's very simple, I don't know if we'll get there today, but we'll try. There's very simple building blocks that in the end of the day you can build all the SCT operators out of. And we're kind of moving our way in that direction. OK, so let's try to gauge this. N dot label operator is 0. So for that guy, you just have in dot partial. There's no label operator piece. And gauging it just takes you to in dot d, which is the full d that had both an ultrasoft and collinear piece to it. And if you look back at how our transformations were defined for UC and U ultrasoft, then this guy is basically just transforming in the way that you would want a covariant derivative to transform, and it does that under both types of symmetries because of the way we set it up like a background field for the n.a ultrasoft. OK, but that's actually not really related to this story because there's no split in the n.p component. So it's really the other components, the perp and the n bar, where we have to pay more attention to what's going on. So if we look at what the gauge transformations mean for those components, it's the same story, but I'm going to write it out anyway. Okay, so this isn't quite how we wrote it before. We wrote it before as a transformation on the A. But if you put the transformation on the A together with the derivative, then you can write it like this. For this piece here, for example, remember what this thing is. This thing here is label operator p bar plus g n bar dot an. Label operator doesn't hit this guy. There's no label momentum in the ultrasoft u, so it just goes through that guy or gives 0, and u dagger is 1. So this piece doesn't contribute there, and this piece transformed in this way already. These ones are slightly more involved, but what I'm saying is just a summary of what we already learned earlier or talked about earlier. And then finally, there's also the ultrasoft transformation. And the ultrasoft didn't transform under the collinear. And of course, it did transform under the ultrasoft. So this is a summary of what we said earlier. So the simplest idea that you would say, well, is just like take these guys and replace this by covariant derivative and that by covariant derivative, right? It's always useful to think about the simplest thing first. So this would be the simplest thing. And that doesn't work. The reason that that doesn't work is that if you look at these two pieces, they don't transform in the same way. So if I were to build operators out of this guy that are gauge invariant, then when I looked at the collinear transformation, because this guy doesn't transform and this guy does, this whole thing is not transforming. So that if I just stuck this guy in, if this guy was invariant, this guy wouldn't be, and vice versa. Okay, so this doesn't work.
Transforms under collinear with its label summing convention.
The ultrasoft under collinear. So this guy didn't transform.
I'm thinking of the top equation in the middle. IND goes under.
Oh, yeah. So then that one's a little, yeah. So you want to know which one? I can look it up for you.
Well, the one you were just pointing out, so that's how the D and the AN part of that transforms, but the A you saw.
Right.
Is there some like?
Yeah, let me remind you. Let me remind myself, and then I'll remind you. So the A ultrasoft never transformed under the collinear, right?
Right. So
yeah.
I guess I don't know how to use this.
And then right. So how does this work out? The reason that this works out is because there was an n.A ultrasoft field in the gauge transformation of the collinear n.A field. Right. That's why it works out. Good, because it'll take me forever to find. All right. So what are we going to do? So we need some kind of compensating object to make these things transform in the same way. And we have such a compensating object. That's our Wilson line. So the Wilson line transformed on one side. And so we can use it to modify those formulas and get a result where both terms transform in the same way. just stick the W in where I need it. In these two terms. And then I have set up things so that the transformation of the two terms are the same. And you could call this, if you wanted to define some kind of full D, then this is the kind of closest that you can get to defining a sort of full D. Okay, so these W's ensure both terms would ensure that under collinear transformation, both terms transform with a UC on the outside. Okay, so we could just stick anywhere that we have an in bar.dperp, we could just replace it by this and then expand out, i.e. we could get a subleading term by just using this operator here. And we know that that is going to be there because of reparameterization symmetry, which was connecting the derivatives, and therefore connects these two. And once we put in gauge symmetry, then this is the form. So if you go back to what we talked about earlier, we said earlier, I said A mu for the full theory, that you could just sort of think of it as splitting between a collinear and an ultrasoft field. And then I said plus dot dot dot. Okay? And I said we'll talk about what plus dot 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 is later. So now is later. What plus dot 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 is terms that you would generate from, for example, the derivatives here hitting the Wilson line or expanding out these Wilson lines of the gauge field. And so those are making it, have terms with more fields than just one field. And so if you thought about the A in here as sort of a full theory A, and the A's in here as the effective theory, you could derive a formula like this one, but it would involve more complicated stuff. It's not good to think about it this way. It's better to think about it in terms of the covariant derivatives, because then you're already thinking about gauge invariance. So this formula was useful earlier, but it's actually these formulas here that are the more useful way of thinking about taking sort of full theory derivatives and turning them into effective theory results. All right, so we can dispense with thinking about the plus dot 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 there because it's better just to think about it in this form where you can write a nice closed expression. OK, so let's do one example of a subleading term. So we had an operator that involved covariant derivatives that were collinear. This one. And if we just use the top formula there, then we know, so this is a term that was in L0. Then we know that there's a term in L1 that looks as follows. And I want to write it out so you sort of see how also the gauge symmetry works out nicely. OK, so using the fact that I can write this guy as a Wilson line, 1 over p bar times a Wilson line, and the fact that I get some Wilson lines when I look at the subleading term. So some of the Wilson lines I get W dagger is 1, and then the remaining Wilson lines are sitting next to collinear fields in such a way that this guy here is collinear gauge invariant. This guy here is collinear gauge invariant. And then there's an ultrasoft transformation that connects up all the pieces. Okay? If we didn't have these W's here, we wouldn't have got those W's in the right spots there. And this operator that I write down here would not be collinear gauge invariant. So this operator is both collinear and ultrasoft gauge invariant. But most importantly, it's linear gauge invariant because of what we did there. And there's no Wilson coefficient to this operator. It's got the same coefficient as the leading order term, so there's nothing non-trivial. We could just use it to get sublitting stuff. Okay? And you could also do similar things for currents. I'm not going to give examples of that, but it's also a powerful tool for connecting coefficients of leading and sublitting operators in currents. Not every operator in the subleading Lagrangian is connected, so there are some that could not be connected at some order, but there's actually more connections than there are in HQET because we have more symmetries.